Okay, good morning, guys. Any questions? So please remember, anytime that you come to the class, there's a sign-up sheet circulating around. Just make sure that you sign it and you don't miss the signature. Right now or after the class is over, you can sign it. Any particular questions about what we talked about last time? Okay, so no questions. So what I'm going to do now is I'm going to very briefly review what we talked about last time, and then we are going to actually continue our lecture. So last time we talked about the definition of the instantaneous value of a power for a particular component in the system, which is basically defined here. Let's see. So if I have an element like this, and I've already defined the voltage and the current of this particular element in accordance with the passive sign convention, I can define that the instantaneous value of the power is just a multiplication of the voltage that I measure by the current that I measure. Then we talked about energy, and to be honest, we don't really discuss or use this energy definition much in this class because we mainly talk about power. Because energy you have to provide 2 timestamps, and that's not very convenient. Then we looked at the average value of the power. Most of the signals that we are looking at in this class are periodic signals, so it's easier to discuss about the average power that a component is consuming over one period. So the average value of the power is like general definition for the average value of any signal. You just look at the initial time and the final time, and usually these are apart from each other by 1 period, and then you basically integrate your signal and then divide it by the duration of the time that you are doing that integration. Then we looked at what if we have a periodic, for instance, current waveform for an inductor, for instance. So as it turns out, if the current of an inductor is periodic, there won't be any power absorbed by that inductor, and as well as the average value of the voltage drop across that inductor is 0. So for instance, if I have, let's say, an inductor in the system, and I'm measuring the current of this inductor, and this turns out to be a periodic waveform like this, okay, so this is 1 period. This is versus time, and this is the current of the inductor. So as soon as I see this, I should conclude that the average power consumed by the inductor is 0, as well as the average value of the voltage drop across the inductor is 0. Okay? So just keep that in mind. And you can make the same argument for a capacitor. So if I have a capacitor which has a periodic voltage waveform, I can argue that the power absorbed by this capacitor is 0, the average power, as well as the average value of its current should be 0. Then we define the RMS value of a signal, which is basically usually defined for periodic signals, and that is, let's say I have a signal of X with a period of capital T, and I'm trying to basically look at its average, its RMS value. If I can find it here. All right, up here. So if I have a signal like x of t, a variable by time, you multiply that signal by itself, so you get x squared, and then you integrate the whole thing over 1 period, and then you divide that by the duration of that period. That is as if you're taking the average value of this x squared, and then you take the square root of the signal in the end. We had an example, and that was a kind of a rectified sinusoidal signal like this voltage waveform over here. And as it turns out, the RMS value of the signal is the peak value, which is Vm or V maximum over the square root of 2. Then we were actually about to start the discussion for another signal, which was like a current waveform this time. The first one was a voltage waveform. This one is a current waveform. This particular current waveform has 2 components in it. One of them is I'm just going to rewrite it over here, 2 sine of omega t You can argue that this could be the fundamental harmonic of your current. And then, in addition to that, you have some higher order harmonic, which happens to be with an amplitude of 3 sine of 2 omega t. So this is the current that you have measured, or this is the result of your simulation, and you would like to find out what the RMS value of the signal is. Again, go back to the original definition. Just multiply the signal by itself. That's why this power of 2 appears here. The square root of 2 appears here. And then do an integration. Now, whenever omega t appears in your signals, it's easier to do, actually, instead of what I've written over here in my note, I would say it's easier to do, okay, multiply the signal by itself, and instead of the differentiation of time, use d omega t. That's much easier. And for that case, you have to go from 0 to 2 pi, okay? And this would be 1 over 2 pi. And then get the square root of that. So if you're integrating versus time, you have to find out what the initial value and final value of the time is with respect to one period. If you're doing with respect to omega t, it's usually between 0 and 2 pi. If you have multiples of omega t as your frequency in your signal. Identifying the period, maybe at the beginning, even before you get into the finding the RMS value of a signal, you have to identify what the period of the signal is. If you look at this first component of the signal, the period of this guy is 2 pi over omega. The period of this guy is 2 pi over 2 omega. And you usually pick the larger value. So between these two values of 2 pi over omega and 2 pi over 2 omega, this is the larger one. So I use between 0 and 2 pi instead of the integration from 0 to only pi. All right. So if you do the math and actually expand this expression over here, you are going to have sine squared of omega t, sine squared of 2 omega t. These are the two components that are going to give us non-zero values over the integration. And this term happens to be 0 because it's just two sine signals multiplied by each other, and you're trying to take the average value of that signal over one period. So this gives you almost 0, basically. Absolute 0, not almost. So the math continues over here. So the only trick is, instead of sine squared, you have to replace with 1 minus cosine of twice the frequency over 2. And so basically I have this term over here, 1 minus cosine of 2 omega t over 2. So that is actually in replacement with this sine squared over here. And then I have sine squared for 2 omega t, so this would be 1 minus cosine of 4 omega t over 2. So this number is actually over is 4. Okay. And if you expand sine of omega t times sine of 2 omega t, it gives you something, but in the end you're going to realize the average value of the signal is 0 anyway, so don't really worry about that part. And again, over integration, if you integrate a cosine of 2 omega t signal over one period, it gives you an average value of 0, so this gives me 0. This one also gives me 0. So the only components that are not really giving me 0 is this 1 over 2 over here, and this 1 over 2 over here, and obviously there is a factor of 4 here and a factor of 9 here. They come directly from this original numbers over here. So in the end, I have, I'm actually taking the average value of a constant value, which is 4 over 2, so this just gives me 4 over 2. So this 4 over 2 over here appears here, and this 9 over 2 over here appears here. So the RMS value of my signal is basically this guy. So that's the RMS value of my entire current that I was actually trying to investigate. If you look at this 4 over 2 or this 9 over 2, as it turns out, 4 over 2 is the RMS value of the fundamental harmonic of our signal. So if you consider this to be your fundamental harmonic, the RMS value of the signal is 2 over the square root of 2. If you look at the square value of that, that gives you 4 over 2. And if you look at the RMS value of this component, which is 3 over the square root of 2, and if you multiply it by itself, it gives you 9 over 2. So if I have a signal that includes a bunch of harmonics, I don't really have to go through this tedious math anymore. I just actually can extend what I just observed right now, and that would be, if I have a signal like this. If I have a periodic signal in general, let's say, using the Fourier series, I can actually expand that to a bunch of components. The first component is the DC value of my signal. So I just highlighted by A sub 0. 0 means the frequency is 0, or basically my signal is DC. And then a bunch of harmonics with an amplitude of A sub n. N is being actually our parameter here, times sine of n omega t. So in our case, for instance, A sub n for n equals to 1 was 2, and A sub n for n equals to 2 was 3. And n was actually a variable between 1 and 2. So if I have a basically periodic signal like this, described by a Fourier series with this expansion, I can find the RMS value of the signal like basically using this expression. So I look at the RMS value of each particular component in the system, and then I get the square value of that, and then I add them all with each other, and then also don't forget about the DC component, and this gives you the whole thing. So let me give you an example one more time. So let's say we are trying to find the RMS value of this signal. This is going to take a long time for me to scroll up and down. Okay, so let's say we have a signal like this. 2 times cosine of omega t plus 5 times cosine of 3 omega t plus, I don't know, 9 times cosine of, 6 omega t. So let's say this is a signal. It could be a voltage, it could be a current, doesn't matter. It's just a signal we have measured, and we want to find the RMS value of this signal. So if you do what I just explained, if you are trying to find the RMS value, what you do is, first of all, let's also add a DC component. For instance, let's say also we are looking at 8 as the DC component of the signal. Okay, so the RMS value would be the square root of DC component squared plus the RMS value of the fundamental harmonic squared, so 2 over a square root of 2 squared, plus the RMS value of the second harmonic that appears squared, so 5 over the square root of 2 is the RMS value of the signal, then squared, plus, you just keep doing that, plus 9 over the square root of 2 squared. Okay? So that's actually how you do that. I don't have the number for this, but obviously you can easily plug this into a calculator and find the final value. So you don't have to go through, multiply the signal by itself and do all those integration. You can just use something like that. All right. So after talking about the RMS value, let's talk about the apparent power. A lot of times we use this apparent power as an indicator of how much power is actually not really exactly consumed in the system. But let me see, I'm on the right place. Yeah. Okay. So if I have a component in my system, let's say this element over here, which has a current passing through it, and there's a voltage drop across this component. And as it turns out, both of the current and the voltage waveforms of this signal or of this element are both periodic. And usually they have the same period. And that's why I'm assuming that this one has a period of t, and this other one also has a period of t. So they both have the same period. The apparent power would be, I have to look at the current signal, find its RMS value, put it here, and I have to look at the voltage signal and find its RMS value and put it here, and then multiply them by each other, and that would be the apparent power associated with this particular component. So it's just basically a definition. Where do we use this apparent power? Most of the time we use it when we want to look at the power factor of a particular element or a source in the system. So power factor by definition is defined actually right over here. Power factor, or PF, stands for power factor, is the ratio between the average power and the apparent power. So earlier we discussed what the average power is, which was the integration over one period of the instantaneous value of the power. And apparent power is already defined up here, which is VRMS times IRMS. And there you go, you are in business. So basically the average power divided by VRMS over IRMS is the power factor for that particular element or source in the system. All right. So please note that all of these definitions are general. They have nothing to do with our signals being sinusoidal. But as it turns out, when you are dealing with the sinusoidal signal or sinusoidal signals in general, and that usually happens in, for instance, when you're dealing with an electric motor, in power systems in general, everything is sinusoidal, or at least close to a sinusoidal waveform. Things may get actually a little easier. So please note that up to this point, nothing was assumed to be sinusoidal. They were periodic, but they were not sinusoidal. They could have been periodic, but a square-shaped periodic, or triangular waveform periodic. They are not necessarily sinusoidal. But let's look at a sinusoidal case. And that is when our current over here is a sinusoidal waveform with an amplitude of Im times cosine of omega t plus some phase, phi. And our voltage happens to be sinusoidal as well, and that has an amplitude of Vm times cosine of omega t plus theta, another arbitrary phase. And t is 2 pi over omega, which is actually the period of both of these signals. Well, we know from before, if you have a sinusoidal signal, it's very easy to find its RMS value. You don't have to go back to the definition anymore. And that is just take the amplitude of the signal and then divide that by the square root of 2. And that gives you the RMS value of the signal. And please remember, this only holds for a sinusoidal signal. So if you have a triangular waveform, do not measure the amplitude and divide that by the square root of 2 and claim that this is the RMS value of the signal. That's not. If your signal is a sinusoidal signal, then get the amplitude, divide that by the square root of 2, that's your RMS. If it is not triangular, if it is not sinusoidal, go back with the original definition. All right, so I can easily find the RMS value of the current, and I can easily find the RMS value of the voltage. Very, very easy, because both of these signals are sinusoidal. So looking at the instantaneous value of the power, I have to go with the original definition. As you can see, I am multiplying the voltage of the signal by the current. So I have basically two cosine terms multiplied by each other. I'm using a trig identity over here, and that turns out to be Vm Im over 2 times cosine of 2 omega t plus theta plus phi plus cosine of omega t minus omega t, which is 0, then theta minus phi, which is the only term that actually appears over here. Okay, so that is actually an expression for my apparent power. If I want to look at the average value of the power, I have to look at the integration or the average value of this apparent power. And this is actually written over here. 1 over the period, integration from 0 to t, as capital T is our period, times including the apparent power. So basically, you're looking at the average value of the signal. As it turns out, this component doesn't have an average value, it's 0. And cosine of theta minus phi is the only component that actually comes out of the integration. So I have, in the end, my average power is basically something like this. Vm times Im over 2 cosine of the difference between the phase angle of the current and the voltage. Or if you look at it, I can actually kind of manipulate this expression and write it in the form of, I'm going to actually expand this 2. Just say Vm over the square root of 2 times Im over the square root of 2. Okay? So Vm over the square root of 2 was VRMS. Im over the square root of 2 was IRMS. And then the cosine of theta minus phi remains over there. So if you look at the apparent power, by definition, it was VRMS over IRMS. And now I have the average power. So I have average power, I have apparent power. I can just divide them by each other and find the power factor. So by the definition that we had earlier, so power factor would be P, basic average power, over VRMS over IRMS. As it turns out, the terms basically, so let me write it over here. So P was VRMS, IRMS, cosine of theta minus phi. All right, and by definition, apparent power was Vrms, Irms. So a bunch of these terms cancel out each other, and in the end, we have just cosine of theta minus phi. And that's the power factor that you're used to see. So remember, power factor is only cosine of the difference between the angle of the two signals as long as they are purely sinusoidal signals. All right, after power factor, the last definition that we have is total harmonic distortion, or THD, total harmonic distortion. And by definition, it is basically a ratio between two expressions. On top, we have all of the junk that appears in the signal. So assume that we have a signal which is supposed to be a purely sinusoidal signal, but in addition to that purely fundamental harmonic, it has a bunch of, like higher order harmonics. So we look at the order of all of those non-desired components that appear in our signal, and then we divide that by the RMS value of the fundamental component in our system. So all the junk on top, the one we desired in the bottom, and that would be our total harmonic distortion. So if our signal is totally purely sinusoidal signal, there's no junk in it, so the numerator is 0, so total harmonic distortion is 0. So now our ideal value for the total harmonic distortion is basically 0. Let me actually have an example for this. But before, okay, let's actually look at the total harmonic distortion of the signal, basically. It's hard to make a judgment for this signal because you may argue that this was my desired signal and the rest of them are the junk. So basically you have to identify which component is the junk, which one of them are not. So let me just rewrite another one that is not ambiguous. So let's say I have a signal like 2 cosine of omega t, and I already know, or I agreed that this is my fundamental harmonic and this is the desired signal. And the junk is, for instance, I have 3 times cosine of 3 omega t plus 5 times cosine of, 9 omega t. So this is my desired signal, and the rest of it is a bunch of harmonics that appear in my signal. And I'm trying to find out the total harmonic distortion in here. So THD. So remember, we look at the RMS value of all of the junk. So this is so I have to look at the RMS value of this. And earlier we discussed how to find the RMS value of a signal which includes a bunch of harmonics. You look at the RMS value of the first component, take the square value of that. Look at the RMS value of the second component and take the square value of that. So that's my numerator. On the denominator, I have my desired signal, which is 2 times cosine of omega t, so I have to write its RMS value. So this would be 2 over the square root of 2. So whatever this expression is going to be our total harmonic distortion. Now remember, if my signal was purely sinusoidal, or this thing didn't exist, this part was 0, so my THD was 0 in an ideal case. All right. Any questions? All right. So these are the definitions that I'm sure you have been exposed to before in the past in a variety of courses. I just wanted to make sure we are all on the same page. So later on, if I talk about the total harmonic distortion or, the RMS value of signal, we all make sure that we have the right definitions and we are going to be using those definitions. All right, let's see what else is left over here. All right. So now we are going to actually get into the core of the class, and that is introducing a bunch of devices that we use in power electronics. The very first one is a diode. Okay. So let's talk about diodes. I'm sure you know all about diodes, but the good news in power electronics is we use ideal diodes, which actually is going to make our life much, much easier. So let's say I have a component, or let's talk about power diodes basically. Well, power diodes and diodes are basically the same. They have the same feature. A power diode is just designed to handle a higher amount of current or block a higher amount of voltage. That's the difference. And they are obviously a little bit more expensive. So remember the original symbol that we used for a diode. Okay, so this is the symbol. You all have seen this before. This is my anode, or A, and this is the cathode, or K. All right, so this is how you label the terminals of a diode. And please remember, for diodes, we always assume that the current flows from anode to cathode. Okay, that's always you assume like this. The current has to flow from anode to cathode. And also, if you're talking about the voltage drop across a diode, it should be the voltage of anode with respect to cathode. So the positive side of this voltage measurement is on the anode side, and the negative side is on the cathode side. Okay. So please remember this definition. This is always, sometimes it gets confusing because the students do some weird stuff. All right. So if I have a diode like this, and the current and the voltage of this diode are labeled in this way, and this is an ideal diode. Okay, so let's talk about a non-ideal diode first. So what you have seen, for instance, in microelectronics is if I want to plot the current that passes through the diode versus the voltage that appears across the terminals of the diode, in a real diode, it looks something like this. Okay? And there is a negative actually area as well, and the diode breaks basically. So here, as you can see, if my diode is conducting some current, there's going to be a little bit of a voltage drop across the diode. For instance, I don't know, 0.7 volts, depending on what diode you're using. And if I apply some negative voltage across the diode, which is basically this area, there won't be any current passing through the diode until a certain point that the diode is going to break, and basically a huge amount of current is going to pass through it. Well, hopefully in power electronics, you never want to get to this point. So you want to actually stay away from that point. Now, if I want to, so this is a real diode. If I want to idealize this, I would say I'm going to neglect the forward voltage drop across the diode. So remember, this was called the VF, the forward voltage drop, which is a very small value. So I just neglect it, and I'm assuming that VF is actually 0. Okay. So if I assume VF is 0, I'm going to actually get to this line. So that means when my diode is conducting, no matter how much current is passing through the diode, there won't be any voltage drop across this diode, or neglecting VF. And this line is already actually sitting here, so I'm just going to rewrite. So this is the volt-ampere characteristic of an ideal diode. Okay? So in this region, I would say the diode is forward biased. Or the diode is on, basically. And in this region, the diode is reverse biased. Or the diode is off. Okay? As simple as it gets. So if mathematically you want to basically describe this, you would say, okay, so in a diode, in an ideal diode, okay, so in an ideal so by the way, this was the ideal diode. Okay, in an ideal diode, what we have is there won't be any voltage drop across the diode if the diode is conducting some positive current. Okay? And there won't be any current passing through the diode if the diode is blocking some negative voltage. All right, so this is a mathematical definition of that VI basically feature that I just drew over there. All right, so this was a diode. You have seen this many, many times before. And let's talk about a component that you probably have not seen before, and that's a Thyristor. Any questions so far? All right, so everything is pretty basic so far. So this could be probably one of the newest thing in this class so far, and that's actually a Thyristor. Or it's called an SCR, which stands for Silicon Controlled Rectifier. So this is okay, or an SCR or a Thyristor. So what is the symbol for this device? It looks like a diode with an extra, basically, pin. Okay, something like this. Again, this is the anode, or A. This is the cathode, or K. And this new guy is called the gate, or just G. Okay? And similar to a diode, the way you define its current is from anode to cathode. So this is current of the, they usually call it current of the anode. And the voltage drop across the component is the voltage of anode with respect to cathode, VAK. Okay. So this is the symbol for this component. And then we have a volt ampere characteristic for this guy. So let's take a look at that. So all right. So if I have not sent any signals to the gate of this component, this component is off, basically. So it's here. So meaning that if I have some positive voltage drop across the component, there won't be any current passing through the component. So in this region, you would say the component is off. Or it hasn't been triggered yet, or the gate hasn't been activated yet. So, and also this region is called forward biasing. Okay? So, if the gate hasn't been triggered before, and I applied some positive voltage across the terminals of this component, there won't be any current passing through the component, unlike a diode. Then, if you are in this region and you trigger the device, so let's say you are in this region, for instance, you are applying, 10 volts across the component, and before triggering, no current passes through the component. But as soon as you trigger the component, that means triggering means sending an impulse of current into the gate, basically. You send a certain amount of current or electric charge into the gate, the device turns on, and then your operating region moves over here, basically. Okay. That means the component starts conducting some current, and there won't be any voltage drop across the component anymore. So it's more like a short circuit, basically. So we would say the component is on or conducting. All right? And if you don't basically apply any gate signal to the system, it can also block negative voltages, similar to just a typical diode. So here, again, the component is off. And it's called reverse blocking. Okay. So I talked about the component could be forward biased, but it's still not conducting. Then you trigger the gate with an impulse of current. The component turns on and conducts current. And no matter how much current, ideally, no matter how much current passes through the component, there won't be any voltage drop across the terminals of the component. Now the question is, when is this component going to turn off? The answer is the component is going to turn off when its current naturally returns back to zero. So this is determined by the rest of the system. And we are going to have an example to actually a little further basically discuss this. So let's say let me just delete this. Just delete. Okay. Never mind. Okay, here it is. So let's have an example. Let's say we have a circuit like this. We have a DC source, and I'm labeling this voltage to be V of source, the voltage of source, like a battery or a power supply. And then in the loop, we have a resistor to limit the current, and then we have a thyristor. Okay? And so we're looking at the voltage of anode with respect to cathode, and this is the current of the loop no matter what component I'm looking at, and this is the triggering signal current of the gate. Okay? So I'm going to draw a bunch of waveforms here. One of them is the current of the gate. And it's like an impulse of, let's say, current. Okay. So at the beginning of the experiment, the gate was not triggered yet. That means, okay, if the gate hasn't been triggered yet, that means we are either here or here. And we are going to actually look at the circuit and see exactly where we are. So if the device is actually off, that means I don't have any voltage drop, I don't have any current passing through the element, so there won't be any voltage drop across this resistor. So the entire voltage of the source appears across the thyristor. So technically, if you look at the voltage drop across the thyristor, it's basically Vs. Okay, the source voltage. Because there is no current in the system in the loop, therefore there is no voltage drop across that resistor. So all of my source voltage appears across my switch. So the switch is off, but as you can see, because there is a voltage drop across that is positive, you would argue that the switch is in the forward biasing region, basically in here. All right. So this continues as long as I have not triggered the gate. So I'll also let me plot the current here. All right. So I just argue that there is no current so far. All right. Now, as soon as I trigger the gate, because right before triggering, the device was in the forward biasing region, the device is going to turn on. That means it is going to go actually in this region now. Okay. So when the device is on, there is no voltage drop across the diode, across the device, so the voltage jumps back to 0. Okay? And what happens to the current? Well, if there is no voltage here across this component, if you look at this loop, this entire voltage appears across the resistor. So the current is the voltage of the resistor divided by the current of the resistor, by the value of the resistor. So the current is going to jump up here. And this is Vs over R. Okay? So everything is matches, basically. Always, when there is a quiz or a homework assignment or something like that, you always in the end have to double check your answer. For this particular thyristor, I have an operating mode that the voltage drop is positive and the current is 0. So I have to go back and see if this really exists. Yes, it exists. Voltage is positive and current is 0. And that was the forward biasing region. Then a gate triggering signal arrived and the system turned on, and then now I have 0 voltage drop for a positive conducting current. And that also makes sense. That's actually, you are basically here. Your voltage drop is 0 ideally, and the current is positive. So that's actually how the device works. Now, this is going to continue forever because there is no way for you to turn the device off anymore. As I said, the device naturally turns off. So if your source is a DC source, this is going to continue forever without you having a chance to turn this device off. Okay? But for instance, assume if my voltage source was a sinusoidal voltage source, you would have, and we are going to see that as soon as we start talking about controlled rectifiers, the story would have been differently. So think of this device as a latch. If the current is conducting positive, it's going to continue the conduction forever unless the situation is somehow the current comes back to 0. Somehow there is a resonance going on, or the current or the source is an AC source or something like that. Now let's look at the same circuit The only difference would that I want to actually include is reverse the component. So it's the same loop. I just have actually flipped this Thyristor. So remember, still I'm measuring the anode to cathode voltage, and I'm interested in the current in the loop. And my source is the same, it's like a DC source. All right, so let's say we are initially here. I'm monitoring my gate triggering signal. At the beginning there is no triggering, but later on I trigger the gate. So at the beginning there is no gate signal. That means the device is off. But I don't really know, is it here off or here off? So I have to basically figure it out. So that's why I'm actually looking at the voltage drop across the terminals of the device and also the current of the loop. This current of the loop is not necessarily the same as the current of the component, because the current in this device has to flow from anode to cathode. Remember, IA is the opposite of I in this case. Okay, so the device has not been triggered yet, so I'm pretty much sure there is no current passing through the device. So the current is 0. Okay, so 0, oops, I think I deleted that. So the current is 0. So if the current is 0, that means there is no voltage drop across this resistor. That means the entire source voltage appears across my switch, and because the switch is flipped, this voltage is basically negative. I'm sorry, I don't have enough room here. I'm just going to draw it here. It's negative Vs. All right. So if you see in this particular case, the switch is off, or the thyristor is off, and it is blocking some negative voltage. So that actually gives you that, hints you that you are actually operating here. Okay. And as it turns out, if your device is in this mode, it doesn't matter if you trigger it, because it's in a reverse blocking mode, it never turns on. So basically remember, the thyristor only turns on if you are in the forward biasing mode, and then you trigger it, you jump here. But if you are in the reverse blocking mode, no matter how many times you trigger it, it doesn't turn on. So triggering this basically thyristor doesn't really make a difference. So you just continue this mode. Okay. So that's actually how it looks like. All right. I have a statement in my notes that I'm just going to read it because it's pretty long. It's going to take me forever to write it over here. But let me just go through it. Okay, here's the statement. Okay. The thyristor is turned on by applying a gate current or a gate triggering signal while it is in the forward biasing state. It's very, very important. Before triggering, your thyristor should be in the forward biasing stage. Otherwise, it's not going to turn on. Like the two examples that we did, we were comparing them. Now, okay, so this is so far how the device turns on. The question is, how long is it going to turn on, or how is it going to turn off? So once the thyristor is turned on, the device continues to conduct, even if the gating signal is removed or disappears. And this is a V, I guess. The thyristor continues to conduct as long as the current remains positive. It's more like a latch. You turn it on, as long as the current is positive, it just continues the conduction. All right? We are going to have an example of how the thyristor is going to turn off when we talk about like half-wave rectifiers or full-wave rectifiers. Just bear with me, and we are going to actually cover it later. All right, any questions so far? Okay, so no questions. So now let's move on to, and by the way, sometimes we call the diodes and the thyristors and power MOSFETs and IGBTs, we call them, all of them, switches. So a diode is also considered to be a switch in power electronics. However, you call it an uncontrolled switch because you don't have a control over the conduction of a diode. It makes its own decisions. A thyristor is called like a semi-controlled switch. You can turn it on if you are in the right conditions, but the device makes its own decision to turn itself off. So far, these are the devices that we don't really have full control over. Now let's talk about devices that we have complete control over. The first one is so let me just write it down here, power MOSFETs or power transistors first. And the first one in this category is power. So actually I'm going to cover them both together. Power MOSFETs oops. Let me clean this. And IGBTs, and we are going to talk about IGBTs in a few minutes. So let's talk about power MOSFETs first. All right, I guess I have to. So let's talk about well, if you are familiar with MOSFETs, power MOSFETs are basically the same as long as the characteristics are concerned. Obviously, there are some structural differerences, like they can handle some higher amounts of current or they can block higher amounts of voltages. But the principles of operation are basically the same. The only difference is if you have a MOSFET in a microelectronic circuit, you usually use it in a linear region. Over here in power electronics, you usually use them in their basically saturation region. So let's take a look at that. Oops. Okay, so let's see what I'm talking about. So let's look at the symbol first. So this is the symbol for our power MOSFET. This is our drain, or just D. Let me use capital D. And then we have a source. And then we have a gate. Okay? And we usually measure the voltage from drain to source. And the current is usually flowing into the drain and coming out of the source. Okay, so these are the polarity of the voltages and say the currents that we consider. And I don't want to confuse you guys, but as it turns out, we always, and just put it in dotted nodes, dotted basically lines. Whenever you make a MOSFET, whether you like it or not, you are also making a diode as well. So you cannot really get rid of this. So diode is called the body diode or the bulk diode. Just remember it's there. We don't really use it very much as far as this class is concerned, but please remember there's a diode always there. You cannot buy a MOSFET that does not include this diode. It's just embedded in it. It's just, you can't get rid of it basically. All right. So this is the volt ampere characteristic that we consider for this MOSFET. If the device is off, it can block positive voltages, okay? And once you trigger the signal or actually activate the gate, the signal turns on and it goes here. All right, so remember this is the ideal behavior. So what are we talking about? We're talking about almost like an ideal switch. If this switch is off, no matter how much positive voltage appears across it, it won't conduct at all. And once it's turned on by the gate, no matter how much current passes through this device, there is no voltage drop across the component. Now compare this with the real MOSFET that you are familiar with in microelectronics. So in a real MOSFET, basically the situation is a little different. So we are still looking at VDS. So this is a real one. ID. The device is off, and then you, for instance, apply particular gate voltage, and you get a curve like this. And then you increase that gate voltage, and you get something like this. And then you keep increasing that gate voltage. So this is VG increasing. VGS, gate to source, increasing. Okay? So this is a microelectronic kind of a MOSFET that you have seen. So this area is called the linear region. This is called the saturation region. As it turns out, in power electronics, we only care about the saturation region. So we care about this line. And then we idealize this line and say, okay, this line in ideal MOSFET goes here. Okay, that means the internal resistance of this MOSFET is almost zero. And obviously, this was the off state. Okay. Now, please remember, MOSFETs cannot block negative voltages. So if I claim that there is a MOSFET that when it is off, it can actually block some negative voltages, that is not true, because as you remember, there is a diode over here. And as soon as the polarity of the voltage reverses, that diode is going to conduct. So MOSFET only works when it only blocks positive voltages. So please remember that. Okay, so this is our ideal power electronics MOSFET. By the way, I forgot to mention that why is it that we idealize these components like the diode or the Thyristor or the MOSFET? For instance, in the diode, why do we neglect this forward voltage drop? First of all, because this is an elementary course, fundamental course. We don't want to spend a lot of time on the non-idealities. But as it turns out, for instance, if your input voltage is relatively large, you don't even need to consider this. So if you are, for instance, processing 100 volts, 0.7 volts compared to 100 volts is like less than 1%. So it makes sense to just neglect it. However, in microelectronics, everything is between like 0 and 2 volts. So 0.7 volts voltage drop across your diode is very important. You have to consider it. But over here, if your voltage level is relatively high, as it turns out, it doesn't really matter if you consider it or not, unless you care about the losses in the system. That's the only case in power electronics that we actually look at these non-ideal features of the components. So that's why we tend to, in power electronics, at least in an introductory class, tend to idealize the components. All right. And by the way, MOSFETs, you know that we have N-channel MOSFETs, then P-channel MOSFETs, then enhancement MOSFETs, depletion MOSFETs. As it turns out, in power electronics, 99 or 95% of the MOSFETs, I'm just going to write it in red over here, they are all N-channel, most of them. And they are mostly enhancement type. All right, so the symbol that I have over there is for an N-channel enhancement type MOSFET, and that's usually the typical dominating kind of MOSFET that's available on the market. All right, so let's look at the kind of the mathematical definition for a MOSFET. So let me write this expression. So if I look at the gate to source kind of the kind of voltage, and if it is greater than some threshold, and that threshold, depending on what MOSFET you are using, for instance, could be 5 volts. If the voltage that I'm applying from gate to source, if it is larger than that threshold, then the switch is on. and therefore ideally there won't be any voltage drop across the MOSFET. Okay, and opposite happens when the switch is off. So if the gate to source voltage is less than that threshold, then the switch is off, and therefore there won't be any current passing through the device. Okay, so this threshold is usually supplied by the manufacturer. It appears on the data sheet. It's usually like 5 volts, or the maximum value of the threshold is usually 5 volts. Let me actually write it over here. This is your threshold voltage. Okay, so if you want to turn your MOSFET on, you just have to apply a voltage from gate to source that is larger than this threshold. And if you want to turn it off, usually I just apply 0 or just short your gate to source. So if you want to look at a little bit of a model for your MOSFET, it looks like this basically. So this is your gate, the drain, and the source. Okay. So from gate to source, we almost have an open circuit kind of a behavior. That capacitor and that resistor, the resistor is very, very large, and this capacitor is a very small capacitor. At least the value of this capacitor usually appears on the data sheet of your MOSFET, very small. Okay, and this resistor is very large. It's as if it's like an open circuit. So if you want to turn your MOSFET on, it's like you have to charge this capacitor so that the voltage across the terminals of this cap is larger than the threshold voltage. In that situation, your MOSFET has turned on. And then this is almost like an ideal diode. It is just highlighting that the current flows from drain to source, not the other way around. And this is your switch. So this switch is actually turned on and off based on this logic that I have actually explained earlier. So if you kind of charge this cap and this voltage is higher than the threshold, the switch turns on. Otherwise, the switch turns off basically. Okay, otherwise the switch is open. Okay, so something like that. So this is an ideal model. All right, any questions? So we won't use MOSFETs until we get to basically DC to DC converters. So the first topic that we have after this, which is rectifiers, they usually don't use MOSFETs. So I'm just covering this for later. So let's have kind of an example of how this component works and how we can turn it on and off. So let's consider our kind of basic circuit. We have a loop. In that loop, we have a resistor to limit the current, and then the MOSFET. Oops. Yeah, that's correct. And we have connected like a let's for the sake of simplicity assume that this is just a DC source, like a signal generator kind of a thing, and it gives us kind of a square-shaped signal. Okay, so this is the gate, drain, source. That's the current of the loop. Okay, so if you have a configuration like this, we are curious to know what happens to the drain to source voltage and the current of the MOSFET, given the signal that comes out of the signal generator, which turns the gate on and off. Okay? So let's say we have a signal generator connected to the gate with respect to the source, and it looks like this, and the threshold voltage is here. That means either we are at 0 level below the threshold, or at a level that is higher than the threshold, for instance between 0 and 10 or 0 and 15 or 0 and whatever the threshold is. And then we are curious to know what the voltage waveform of drain to source looks like, and also what the current passing through this loop, which happens to be the current of the MOSFET as well, what that one looks like. Okay. So initially, we are applying 0 to the gate with respect to the source. Oops. And going back to this expression over here, we are actually here. The voltage that is applied from gate to source is less than the threshold because it's 0. And that means the switch is off. If the switch is off, that means we are in this region. That means there is not going to be any current passing through the switch while it is blocking positive voltages. All right. So the current is definitely 0. So the current is 0. Oops. Oh, I don't know what is going on here. Okay, the current is 0. So let's look at the drain to source voltage and make sure it's positive. If the current in this loop is 0, as it turns out, there won't be any voltage drop across this resistor. Therefore, drain to source voltage will be the same as the source, and the source voltage is positive. So we get a positive voltage drop here. So, and that is actually in agreement with our volt ampere characteristic. If the voltage drop is 0, if the voltage drop is positive, then the current is 0. Otherwise, we cannot have a negative voltage drop across the component because of that anti-parallel diode. All right. Now, as soon as we apply some voltage from gate to source, which is larger than this threshold, the device is going to turn on. And if the device turns on, as you can see, it behaves like a short circuit. If the device is on, there won't be any voltage drop across the component as long as the current is positive. All right, so let's see that. So the voltage drop is going to jump to 0. All right, oops. So the voltage drop is going to jump to 0, and let's see what happens to the current. If this voltage drop from here, from drain to source is 0, that means we are in this loop, we have just a source and a resistor, and the current of that resistor is going to be Vs over R. All right. And this is in agreement with that volt ampere characteristic. Positive currents, 0 voltages, and that's how it is. And this cycle kind of repeats itself because our gate signal is kind of a periodic kind of a waveform. All right, so this kind of continues. So if you have a MOSFET and you want to test it, this is a very simple circuit. You can just build it in the lab and actually test your MOSFET and make sure it is functional. It's working well. One question that usually comes up is, what if as we are basically providing this gate signal, let's say we are at this time instant, and a particular gate signal is applied to the system. What happens? We kind of disconnect this gate. Okay, we disconnect the system that is connected to the gate. What happens? As it turns out, right before that, you had actually charged this capacitor. So the MOSFET continues to basically be on, okay, even though you have physically disconnected your gating signal. If that disconnection is happening when you're right before that, your gate signal was positive, like here, the device continues to turn on. So just remember that. The other thing that you guys need to remember is you need kind of a voltage source that holds to operate with the system. It's not like that SCR that you just send an impulse of current and then before that the current doesn't really matter anymore. So if you remember the SCR one, we just send an impulse of current and right after that just current come back to zero. But here if you want to maintain your component to stay on, you have to basically hold this voltage. You cannot return back to zero and assume that the device is on, still on. As soon as you come back to zero, the device turns off. So if this conduction is important to you, you have to make sure you are maintaining this gate to source voltage throughout that subinterval. So this happens a lot in the lab. The student, like they are trying to shut down their device, the first thing that they do is they turn this signal generator off, and if at the time that they are turning it off, the signal was high right before that, your MOSFET is still on. So you have turned your signal generator off, assuming that everything is off in the system, but it is not really off. It is actually continuing to conduct the MOSFET. So please remember, if you want to turn things on, dial down this supply voltage over here. When the supply voltage is down to zero, then you can disconnect or turn your signal generator that is connected to your gate. So a lot of times happen, they basically blow up a MOSFET or they kill it. That's because it's all of a sudden turn their gate to source basically signal generator. So as I said, they have also continuous conduction characteristic. If you charge this cap and leave the component by itself, this switch is turned on already. So it just continues to conduct until you discharge this cap basically. All right. Any questions about MOSFETs? Okay. So as it turns out, MOSFETs are relatively fast devices. You can go up all the way up to switching frequencies of, let's say, 100 kilohertz, 200 kilohertz. I mean, as we go ahead, they are getting faster and faster. So maybe 5 kilohertz, 500 kilohertz, or maybe 1 megahertz, or even higher than that. But the problem is they cannot handle a huge amount of current. By huge, for instance, I'm talking about 1000 amps or 200 amps or things like that. And they cannot block large voltages, for instance, 600 volts, 1000 volts, things like that. So MOSFETs are kind of ideal semiconductor switches for kind of low power, like 50 watt, 100 watt, 200 watts kind of applications. But if your power is a little bit higher than that, there is a device, another device, which is called an IGBT, pretty much similar to a MOSFET, but can handle higher amounts of current and can block higher amounts of voltages. So let's take a look at this one. All right, so IGBTs. But they are not as fast. Okay. So basically, they are just a basic bipolar transistor. However, the only difference is on their gate signal, there is a MOSFET embedded in there. And as you can see, when the MOSFET is on, as soon as you charge this cap over here, even though you are maintaining your gate to source voltage, the device is not, the gate part at least, is not consuming any power. All you have to do is just to maintain the state of charge of that cap and the device is going to be on. Bipolar transistors are not like that. They need a continuous amount of current going through their base to remain on. And that actually translates into power losses. To avoid that, they have added that MOSFET to the gate part. So on the gate part, you see the behavior of a MOSFET. So if I look at the symbol for this device, see, we are kind of drawing a little bit of like a capacitor over here, which is similar to this cap that we had for a MOSFET. Here we also have like a semi-capacitor over here. The indication is from gate to source, we have a cap basically. All right. So this is not called base anymore, it's called the gate. But these two guys are the same, the collector and the emitter. Okay. the current of the collector, and when it comes to measuring the voltage, we always look at from collector to emitter. All right, so this is just C, and this guy is just E. Okay, so the volt-ampere characteristic, the ideal volt-ampere characteristic of this component is exactly the same as the MOSFET. So if the gate has not been activated or the gate to emitter voltage is 0, you can expect the device to basically tolerate or block some positive voltages. And if you are in this region and kind of activate the gate signal, you basically have an ideal, like a short circuit path, and that means the device is on or saturated. Okay? And again, we have NPN and PNP transistors, but usually they are NPN transistors. So this particular one that I drew over here is an NPN IGBT, which is usually the case in industry. So this is an NPN. So if you look at the basically logic behind this device is very similar to a MOSFET. If the voltage that appears or applied from gate to emitter is larger than a certain threshold value determined by the manufacturer appears on the data sheet, the switch is on. And therefore, in an ideal case, you won't observe any voltage across the terminals of the device. It's like a short circuit when it is on. And if the gate to emitter voltage is less than that threshold, usually 0 or sometimes some negative value, the switch is off. Therefore, the device is blocking some positive voltages and the current is 0. Okay? So if you look at the model, it's almost like the model of a MOSFET. I'm not going to draw it. It's basically the model that you can assume for the component is pretty much similar to this model that we had for a MOSFET. From gate to emitter, we have like a cap. If you charge it, the device is on. If you discharge that cap to 0 or some little negative voltage, it turns off. As long as this course is concerned, MOSFETs and IGBTs are identical, meaning that you can unplug one of them from your circuit and plug it in with the other one. And that's actually the case in most cases, unless the voltage and current rating of the devices are drastically different. Their gate signal requirement is pretty much the same, and their features are a little bit, ideal features are almost the same. So as long as this class is concerned, we just assume they are the same. But in practice, in industry, they are not the same. Let me go back to this little table that I have over here and discuss that. Okay. So in terms of switching frequencies, MOSFETs are faster devices, so they can handle higher switching frequencies like 100 kilohertz, 200 kilohertz, 500 kilohertz, maybe 1 megahertz. But IGBTs are not that fast, so they can handle maybe 10 kilohertz, 50 kilohertz, maybe 100 kilohertz. So in terms of switching frequency, MOSFETs are faster. In terms of voltage rating, MOSFETs, you can find a MOSFET on the market that can handle up to 1000 volts, blocking voltage. But for IGBTs, you can, I guess this node was prepared several years ago, but now you can even find IGBTs that even can handle more than this, maybe 5 kilovolts. Recently I heard about a 15,000 volt kind of an IGBT, so they are higher powered, they are used for higher power applications. Okay, so to summarize, okay, I guess we're out of time. I'm just going to go through the summary next time. and then we are going to start the core of this class, the first category of converters, which are actually AC to DC rectifiers next time. All right, so see you guys next time. Thank you.